शाम रैंडमली मैं जो हूँ जाऊँगा लेक्चर्स के ऊपर से, तो देखते हैं क्या क्या आता जाता है, उस तरीके से रिवाइज करते जाएंगे। लेक्चर 5, 6, 7, 8, ठीक है। तो ये बेसिकली प्योर सब्सटेंस के बारे में, जिस भी केमिकल की अ, किसी भी सब्सटेंस की फिक्स केमिकल कंपोजिशन है वाओ, तो बेसिकली प्योर सब्सटेंस कहलाएगा वो। क्या एयर भी प्योर सब्सटेंस है? बिल्कुल एयर भी प्योर सब्सटेंस है, क्योंकि उसकी कंपोजिशन जो है वो थ्रू आउट जो है सिमिलर रहती है। Pure substance does not have to be single chemical compound, a mixture of various chemical compounds से हो सकता है अगर तो वो homogeneous। For example, a mixture of several gases, but it is often considered to be pure substance because it has uniform chemical composition. However, a mixture of oil and water is not pure substance. If oil is not soluble in water, it will collect on the top of the water, forming two chemical dissimilar regions. So phases of pure substance basically in the solid phase, liquid phase, and gases. Uh, so there are a few terminologies which is termed as compressed liquid, and liquid which is not about to vaporize is called compressed subliquid. Subcooled liquid, saturated liquid which is about to vaporize is called saturated liquid. And 1 atm pressure and 100 degrees centigrade water exists as a liquid that is ready to vaporize. So 1 atm and 100 degrees centigrade. Saturated mixture. In saturated liquid vapor mixture, the liquid and vapor phases coexist. So this is basically a region which comes inside the dome. Basically, this is a liquid vapor mixture, also called the wet region. Saturated vapor, the vapor that is about to condense, is called the saturated vapor. Superheated, the vapor that is not about to condense, is called superheated vapor. As more heat is transferred, the temperature of vapor starts to rise, superheated vapor. So here it was 1 atm 300 degrees centigrade. The temperature remains constant at 100 degrees centigrade until the last drop of liquid is vaporized. So these are different phases: compressed liquid, then this is a saturated liquid, then the saturated liquid vapor mixture. This is vapor, this is liquid. Then all the vapor vaporizes, saturated vapor. This is superheated vapor. So there are different terms related to saturation temperature and pressure. So there is saturation temperature and saturation pressure. At a given pressure, the temperature at which a pure substance changes phase is called the saturation temperature. And likewise, saturation pressure at a given pressure, at a given temperature, the pressure at which a substance changes its phase is termed as pre-saturation. For example, at pressure of uh, 1 atm or 101.325 kilopascal, T saturation is 99.97, and conversely at temperature of 99.97, the P saturation is 101.325 kilopascal. So this is saturation temperature and saturation pressure. So the temperature at which water starts boiling depends on the pressure. Therefore, if the pressure is fixed, so is the boiling point. So here you can say as we increase the so if we increase the pressure, the boiling point of the water also increases. So this is called the property diagram. Here this phase is called the compressed liquid. Here it is called the saturated liquid, saturated vapor line. Inside there's a wet region, saturated liquid and vapor both exist, and here it is superheated. Critical point is the point as the phase change process is carried out at a higher pressure than 1 atm water boils at higher temperature than specific volume of saturated vapor. So basically, this is the region at which uh, there are a few standard values of 22.06 First at the critical point, and the temperature is 373.95. The triple point is the point where all three phases exist. So this is about the latent heat. The amount of heat energy absorbed or released during a phase change process is called the latent heat. For example, amount of energy absorbed during a melting is called latent heat of fusion. And enthalpy, as you know, is equal to internal energy plus flow energy. So its unit is kilojoule per kg. Capital per unit mass will be kilojoule. These are property tables we use. A1 for molar mass is A for saturated water if temperature is given. A5 when pressure is given for the saturated water. A6 for superheated. A7 for compressed. And we will be doing approximations against A4. Only A4 can be approximated because the pressure ranges are not very high in the compressed liquid steam table charts. So we will approximate it to A4 table only. A4 to A7 are commonly called steam tables. They look like this. Steam table look like this: saturated water, and this A4 means temperature will be given to us. So if two properties are known at a state, then we can find all the other properties as well. So if, for example, if temperature is known and other property is saturated liquid, means which we can use this table. So we can find a saturation, a pressure, specific volume, and internal energy for the liquid state and vapor state, likewise enthalpy and entropy. So there's a term called enthalpy of vaporization. HFG is it's used in numericals. It's basically Hg minus Hf. So basically, this is the amount of energy needed to vaporize unit mass of saturated liquid. So you have to vaporize the saturated liquid at a given temperature or pressure. So the amount of energy needed to vaporize unit mass of that saturated liquid is called the latent heat of vaporization, HFG. Then there's a term called quality of. It is basically mass of vapor over mass of total mass. The total mass can be calculated as mass of liquid plus mass of vapor. The quality lies in between these two lines. Here is saturated liquid, here the quality is 0. Here the quality can be max, and which is 1. In between there is a wet region. For that we find the quality. The more close it is to the saturated vapor line, it will be like this: 0.9, 0.8, like this. Further it comes to this, it approaches 0. So quality has no significance for saturated mixtures. Quality has significance for the saturated mixtures only, for the wet region. It has no meaning for the compressed liquid or the superheated region. Total volume is equal to volume of saturated liquid plus saturated vapor. So we know the specific volume is equal to volume divided by specific volume is equal to volume over mass. Any quantity divided by mass will be specific. Mass, total mass, we know like this. So this is another quality formula: Vf minus Vf over Vfg. So likewise, we can find there's a formula for finding the any property at the wet region, which will be, first you will write down the, for example, if you want to find H4 state, which lies in the wet region in between here. So you will first find its enthalpy of the saturated liquid plus quality at that state and latent heat of vaporization, HF, which will be Hg minus Hf. So you can similarly write it for the internal energy and entropy as well. Same relation. So this is for the superheated vapor. So if P saturation is greater than the P, and higher temperatures mean the temperature is high, then the T set. For example, if the T saturation for the water is 100 degrees centigrade and the temperature is 350 degrees centigrade, so mean the temperature is given greater than the T saturation at which it starts boiling. So it will be at superheated region. For example, P saturation. So P saturation is 1 atm. So it will be greater than the P, which is here. So this is a table for saturated. We will be given pressures, and against them we can find these properties: pressure, volume, internal energy, enthalpy, entropy. For compressed liquids, however, pressure will be greater than P saturation, and T saturation will be always be greater than P. As you can see here in this region, it's very obvious that T saturation, which is 100 degrees centigrade, will always be greater than T. So that will be the indication of compressed liquid, and pressure will be higher than the P saturation. Here the summary of the properties of pure substances. Compressed liquid T saturation will be high, and superheated T will be higher than T saturation. Saturated vapor T saturation at P saturation, liquid T saturation at P, and when there is a mixture, we will also be T saturation. So this is an ideal gas. An equation that relates pressure, temperature, and specific volume is termed as the ideal gas equation. So it will be used for the ideal gases. Specific volume can also be written as PV is equal to mRT. So if volume is divided by mass, it will become specific volume. Ideal gas relation. A gas that obeys this relation will be termed as ideal gas. So this is universal gas constant. This R is equal to RU over Rm. This R can be different for different working fluids, gases, but this universal gas constant will be always be constant. So the mass of the system is equal to the product of its molar mass and mole. Mole is equal to mass divided by molar mass. Specific volume, volume divided by mass. So we can simplify these equations. This equation is equal to mRT. M is a constant, R is a constant. So PV is equal to T. T will come this side. For state 2, it will be P2 V2 over T2. This relation comes from the ideal gas equation for the fixed mass. Or if you know the properties P1, P1, T1, P2, and V2, you can find other quantity as well. Basically, ideal gas is an imaginary substance which obeys this ideal gas equation. So at higher pressure and low temperatures, the gas does not behave as an ideal gas. However, at higher temperatures and low pressures, the gas behaves as an ideal gas. So basically, if the temperatures are high and pressure is very low, gas can behave as ideal gas. However, if the pressures are very high, temperature is low, that will not behave as an ideal gas. So at high pressures below 10 kilopascal, water vapors can be treated as an ideal gas regardless of its temperature. At higher pressures, however, the ideal gas assumption yields unacceptable errors, particularly in the vicinity of critical point. So you can see in these tables and predict the behavior of an ideal gas. Another term is called the compressibility factor, Z. Basically, it's from the ideal gas and real gas. The deviation for the deviation of ideal gas behavior at a given temperature and pressure can accurately be accounted. So basically, for the deviation purposes, we encompasses a factor called a compressibility factor, which is PV is equal to ZRT and Z is PV over R. The Z is a volume of actual over volume of ideal. So Z will always be 1. Z is 1. It will become an ideal gas. It will become an ideal gas. So further away is 1 Z from 1. It means the gas deviates more from the ideal gas behavior, and thus it's not an ideal gas. So these are other terms: critical temperature at critical pressures. Gas behave differently at given temperature pressures, but they behave very much the same at temperature pressure normalized with respect to their critical temperature. So for the normalizing purposes, we divided by the critical pressure and critical temperature, and the term will be called as reduced pressure and reduced temperature. So basically, if temperature is divided by its critical temperature, it will become reduced temperature. So at very low pressures, all gases approach ideal gas behavior. So saying this non-ideal gas behavior at the critical point, gas deviate from the ideal gas behavior the most in the neighborhood of the critical point. So this is the most deviation point of for the gases from the ideal gas behavior. So here is the problem saying determine the specific volume of refrigerant 134A at 0.9 Pascal and 70 degrees centigrade based on ideal gas equation. Generalized compressibility charts. For that, we will use these relations, compressibility charts. And I also remind the percentage averages. So specific volume for R31 against these two parameters will be first point from that tables, then ideal gas equation, then compressibility charts. So from table A1 for one refrigerant 134A, you can find the critical pressure, temperature, and R value. From property table for 134A A13, basically pressure is very high. Pressure is very high. So we will go to the superheated region, and against these we will find specific volume. And from ideal gas equation, V is equal to RT or P. We know the P. We know the P is 900 kilopascal. We know the R. We know the T. You can find V from the compressibility ideal gas equation. For the percentage error, which is exact minus approximated divided by exact. So we can take the modulus. You can add approximated minus exact over approximated or exact. So there is a modulus, it doesn't matter, negative sign will go away. Multiply by 100, you will get the percentage error. So exact is coming out to be from this is the exact from the property tables, and from the ideal approximated is this one. So 13.3 is the percentage error, which is quite a lot. That's why we incorporate the compressibility factor. So we found like this: critical temperature, critical pressure, critical volume. So like this, we go to the superheated refrigerant. Pressure was given. So T saturation is 31.3, but look at our temperature. T70. So T was greater than T saturation. Means it is superheated. Okay. Determine the specific volume of African 134 vapor pressure temperature given ideal gas. Okay, we will again from the compressibility chart. What we will do, we will find critical temperature, and reduced pressure. So we will find critical and from table A1 pressure and temperature are given. We find reduced pressure and temperature. So now we will go to the compressibility chart. So figure 120. I think this is figure A28 at PR and TR 0.92 and Z is equal to 0.89. So this is basically reduced pressure, and this is these lines are basically reduced pressure, and we can find reduced temperature as well. These are reduced temperature lines. So a reduced pressure was 0.22. This is 0.22. We go up here, and reduced temperature was 0.92. So this is 0.9. 0.92 will be somewhere here. Then we will cross it. So compressibility factor was coming out 0.9, 0.89. So this was for specific volume, compressibility factor divided by V ideal. So that was our specific volume. To calculate the percentage error, we use this relationship V exact minus approximated divided by exact. So exact was found out using the tables. This is the approximated from the tables. And so look how much percentage error is being reduced by incorporating the compressibility factor. So that's the use for compressibility factor. We have to know how they have been add use. So V is equal to V actual over V ideal, as we discussed earlier. So we can take this V ideal over here, so this relation will come out. So Z we know V for V ideal. I don't know where this V ideal come from the previous question or somewhere else. Z was calculated, and V ideal I think this was calculated V ideal 0.03105. Against this pressure and temperature, you will find these values. So V is coming out like this 0.02, but this value is not like that. This value is exact value. This value is ideal, and it would have been found out by using this. P is equal to RT. P, T, R from the table. We can find V1. This will be the ideal one. Look, this one. That's how you find the ideal. 0.0310. 0.0310. Yeah. So the volume meter cube tank contains 1 kg of refrigerant at 100 degree, 110 degree centigrade determine pressure of refrigerant. So we need to find the pressure using ideal gas equation, conversibility chart, and refrigerant tables. Oh, okay. So the pressure P is given and volume, specific volume is also given. And pressure and specific volume are given. 1 kg of refrigerant. Okay. Temperature is given. We will first use from table A1. We will find because it's asking us to find compressibility. So we will find critical temperature and pressure for calculating the reduced temperature and pressure to go to the chart compressibility and in order to find the compressibility factor. So from the property tables from superheated. So as you can see, 110 degrees centigrade, and we go to the superheated. A13, T is 110 degrees centigrade, and volume is given. Specific volume we find pressure. From the idealized, P will come out in kilopascals, in R is in kilojoule per kg. So R is given, T is given, and specific volume will put from here. We'll find P. This will be ideal P, like this. Pressure, temperature was given, and specific volume was also given. And against that, we found out the pressure. Like this. Okay, from a meter cube tank contains 1 kg, so it will become specific volume per kg. Temperature is given. Okay, this is the same problem. Now we will find T reduced, T V reduced. So there's an expression V reduced is equal to V actual over R T critical over P critical. You know, T critical, P critical, R V actual. This is V actual. We calculated from the table of the given one. Then we find P reduced from the compressibility chart using VRTR. So this is T reduced, this is V reduced lines. By intersecting them, we can find the reduced pressure. So this was reduced pressure. Reduced pressure expression is P over P critical. We know the critical, we know the P reduced, we can find the pressure. The pressure was asked. We calculated the pressure. In previous problem, we calculated. It asked us to find the percentage error in specific volume. So basically, there are other equations of the state van der Waals equation. We have expression. These are constant. We find them by using the expressions. These are given in the exam. So you just have to plug in the values. Brady-Bridgman equation. Again, this A and B are found out by using this, and these A and B are given in the table. Just have to plug in the values, and you can calculate the pressure. Like this, you can find A naught, A, B naught, B, C for different gases. So this will be used for Brady-Bridgman. And this is Benedict-Webb-Griffin equation. And find all A naught, B constants from here. So volume is given. 100 kg of mass is given. Temperature is given. Determine the pressure in the tank using ideal gas equation, van der Waals equation, Boltzmann equation. Compare your result with the actual. This is actual exact pressure value. So from ideal gas, PV, you can find from table A1 these constant values. V is equal to volume divided by mass, specific volume. V specific volume is equal to RT. We can find the P. Then we can calculate the percentage error by subtracting the actual minus approximated our actual into 100. From the van der Waals equation, we'll find this theoretical physical limit below. If calculated this constants to plug in the values A and B, we know the volume, specific volume, we know the R, we know the T. This is specific volume and calculate into like this, divided by into the mass by 100. Whenever volume is given, we can convert it into and the specific volume, and these two quantities are given. You just have to divide volume by mass, you will get the specific volume. For pretty Briskman, table 3.3 for nitrogen, because the working fluid is a gas is nitrogen, we find these constants, plug in the values, and then we will get these percentage error as well and this pressure from this equation. So for nitrogen and British Briskman, A naught A, B naught B, C, A naught A, B naught B, the specific volume, the R use of universal constant, the B, C, V, B, B, you can find B. So this is basically the same concept given in the previous slides, same slide as well. This is so yeah, this was it. So we covered 5, 6, 7, 8. We move it to the 10th section. 6. So the same